Hello, today my lecture will be focused on design of lacing systems. In fact, this is a continuation of the previous lecture. In previous lecture, we have discussed about different aspects of design criteria of lacing systems. In codal provisions, different guidelines have been given. So, according to that, we have discussed what are the guidelines we have to maintain for design of lacing systems. Today, first I will just give an short overview of the yesterday's lecture, that means the design steps which we have followed, which we have discussed for designing of lacing system. Then I will go through one example through which we will be clear to understand how to design a lacing system. The example will not only design the lacing systems only, but also it will design first the built up sections, means for a given load and for a given dimension, dimension means the length of the column, what should be the appropriate built up sections, and then what should be the orientation, whether it is back to back or front to front, whether it is channel section or I section, all these things we will discuss. Then we will design those built up sections. After that, we will design the lacing systems, including the connection between the main frame with the lacing. I hope with this it will be clear that how to design a built up section with the lacing. So, in last lecture we have discussed about design steps. Those steps first I like to remind again, because these steps will be required for working out the example. First, what step we are making, that choose the lacing system, that means either it is a single lacing or double lacing, that we will first choose. Then what we will do, we will choose the angle of inclination with the axis of the compression member. So, this is the first thing we will decide, that means first we will choose whether it is double lacing or single lacing, then we will decide some angle of inclination. In fact, in codal provision we have seen last day that the angle of inclination should be in between 40 to 70 degree. So, in between some angle of inclination we will choose. In next step what we will do, that for a given shape we will find out the gauge distance on each side and find the distance A between the rivet center, then compute the spacing. That means, first we will find out some shape, that means on the basis of the availability in the market or on the basis of the choice of the designers, we will find out the built up section shape, whether it is channel section or I section or combination of channel and I section, or say combination of angle section, that we will first decide. Decide means we will choose, and then we will find out the distance A. That means, suppose if this is a channel section, we are choosing say back to back channel section, then we know what is the gauge distance. We know gauge distance, and we will find out the spacing for the optimum use of the material, and then we will find out the A. A means basically A will be S plus 2G, that we will find out, right. Next what we will do, next we will check that slenderness ratio, whether L by RC minimum is exceeding 0.7 lambda max or not, and 50 or not. That means, we have to check this one, that this should not exceed more than 50 or more than 0.7 lambda max. Then in step 4 we will find out the length L of each lacing between the inner end rivets, and then find the effective length. Length L means, suppose two main frame is there. Now, if we have to find out the length, this will be the length. So, the moment we know this distance A, we can find out the length L, because we know the angle of inclination. So, length L we can find out, and then as per the boundary condition, end condition, we will find out the effective length, and this has been guided in the code. Then in next step 5, what we will do, that we will select some rivet diameter, that some rivet diameter we will choose, and accordingly we will find out the width of the lacing, which is given in the codal provision. So, we will find out the minimum width, and then we will find out, we will adapt some width through which we will go on designing, right. And then the number of rivet required, that also we can find out, right. Next what we will do? Next we will find out the thickness. As we know from the codal coefficient that thickness should be greater than L by 40 and for single lacing system and L by 60 for double lacing system. So, accordingly we can find out the thickness T, and then what we will do? We will calculate the maximum slenderness ratio of the lacing and check whether it is less than 145 or not, right. That means the slenderness ratio, how do we calculate? We will calculate the radius of gyration of the section which we are going to adapt. Radius of gyration means we know T and B, thickness and width of the lacing. So, we can find out the radius of gyration, that means I by A, root over I by A. So, from that we will see whether it is exceeding 145 or not, and accordingly we will adapt. If it is exceeding 145, then we have to increase the dimensions so that L by R ratio, the slenderness ratio become less than 145. In step 8 what we will do? We will find out on the basis of the calculated lambda, we will find out sigma AC. Sigma AC from where? From table 5.1. In table 5.1 of IS 800 1984, we will get the allowable compressive stress sigma AC on the basis of lambda and the type of steel we are going to use. So, on that basis we will find out sigma AC, and then what we will do? Then we will calculate the transverse shear V, which is 2.5% of the axial compression. So, transverse shear we can find out, then we can find out F in each lacing, whether it is double lacing or single lacing. Accordingly, F we will find out as we have shown earlier. Then what we will do? Then we will find out the compressive stress and tensile stress, and we will check whether it is exceeding the permissible compressive and tensile stress. If it is exceeding permissible compressive or tensile stress, then we have to increase the dimension, otherwise it is okay, right. And in step 11 what we will do? Then this is the last step where we will design the end connections. End connections means whether we are going for welding connections or riveting connections. So, accordingly we will design number of rivets, how many will be, that we will find out, and what type of riveting we are doing. Riveting means what type of, means what is the configuration of rivet joints. Accordingly the force will come, and accordingly the number of rivets can be find out, right. So, with these steps we can design a lacing system. So, in this example let us see how to design the lacing system. That a built up compression member having effective length of 6 meter and carrying an axial compressive load of 100 kilonewton. That means axial compressive load is 100 kilonewton, this is given, and effective length LE of the compression member, that is given as 6 meter. These are the two things which has been given. Now, we have to design the member using first single lacing system, then double lacing system. Two things we will see. If we use single lacing system, how design we are going to follow, and if we use double lacing system, how it is differing from the single lacing system design procedure, that we will see. So, to differentiate the two things or to understand properly both the things we will do, right. For the same problem we will first design using single lacing system and then using double lacing system. So, these are given, effective length and total load is given, and now it is the choice of the design engineer what type of section he is going to adapt, whether channel section or angle section or I section, it is up to him, and it is of course up to the availability of the section in the market. The section which are available in the market, on that basis we generally used to choose what type of things we are doing. Now, say let us, we are choosing two channel section back to back. So, let us first use that two channel section we are using, and that we are using back to back. So, this is the first criteria we are assuming. Okay. Now, from this what we have to do? Now, we have to find out the spacing through which the applied load can be carried out without any problem, and second is whether it will be back to back or front to front. Now, generally back to back channel is preferable from the designer point of view. From the maintenance point of view, we have shown earlier that why channel section back to back is preferable. So, we are preparing this one, and another thing is we have to assume the slenderness ratio, because on that basis we have to find out the size of the section. Now, in the codal provision it is given that if we assume slenderness ratio around 50, then we can find out an optimum size of the section. So, at the starting point we are choosing the slenderness ratio as 50, because for built up section generally slenderness ratio become less, right. So, with this we can find out the value of sigma AC, that is the permissible compressive stress, which we can find out from table 5.1 of IS 800/1984 for a particular grade of steel. Say suppose grade of steel we are going to use as Fy is equal to 250, right. So, from table 5.1 I can find out sigma AC, the compressive stress allowable is 132 MPa, right. Now, the allowable stress as we are getting, we can find out the gross area required. The area required for the section is this. So, this is the basically this is P by sigma AC. P is 1000 kilonewton and sigma AC is 132. So, from this we are getting 7576 millimeter square. The area required is 7576 millimeter square. Now, we will see two channel section as we are going to use. So, what channel section will be preferable to adjust this much area, right. So, if we use say ISMC 300 with a weight of 35.8 kg per meter, then we see the gross area of each section is given as 4564 millimeter square, right. So, total area we can find out as 2 into this is equal to 9.28 square millimeter. So, 9128 millimeter square area we are going to use, whereas we need 7576. That means we are using little higher side. Now, with this channel section we have to check whether the allowable stress is greater than the developed stress or not. So, for this now actual section we know, so we can find out the lambda which is slenderness ratio. So, slenderness ratio L by R means in this case R will become RXX, and this is L is effective length is 6 meter and R is 118.1 millimeter, which we can find out from IS 800/1984, and then it is coming lambda as 50.8. Remember, we have assumed lambda as 50 and now it is becoming 50.8, right. So, actual lambda is becoming 50.8 and the sigma AC, the allowable compressive stress, is becoming 131.2 MPa. This we can find out from table 5.1, right. So, now what we will do? Next we will find out the required area, because now we know what is the slenderness ratio actual and what is the actual load, and so what should be the required area. So, required area will be the actual load by the allowable compressive stress. So, that is coming 7622. This is the area required and we are going to provide 9128 millimeter square. So, this is perfectly okay. That means the required area is required 7622 millimeter square and we are going to provide 9128 millimeter square. So, in this way it is okay. So, we can say that the section chosen is safe. Thus, we are providing two ISMC 300 at 35.8 kg per meter back to back. So, this is fixed now, right. So, this is one thing unknown, that is the what is the built up section configuration and what will be the size of the built up section. These two things we have decided. One is we are going to use channel section back to back and size is IS MC 300, this size we are going to use. Now, we have to decide what is the spacing between two channel, right. So, for spacing what we will do, that we will try to find out that the maximum strength, that means the spacing should be such that Ix will be equal to Iy, so that the maximum strength in both the direction we can find equal, right. So, if we make Ix is equal to Iy, that means Ix is basically 2 into Ixx, 2 into individual Ix, right, 2 into this is the moment of inertia about x direction of a individual section. So, this is Ix. Similarly, Iy we can find out. Iy, what will be Iy? If we see the orientation of the member, we will see what will be the Iy. Let us see, say this is two channel placed in back to back. So, what will be Iy? Iy will be the individual Iyy plus this is Cy and this is S by 2, because total is S, right. So, Cyy plus S by 2 whole square into A, that means Iyy plus A R square into 2. So, this will become total Iy. So, now if we make Ix equal to Iy, then we can find out the value. So, Iyy we are getting this, where S is unknown, and if we make equal, we can find out the value of S, which is coming 183 millimeter, right, because Ix is 2 into this 6362.6 into 10 to the 4 and Iy is 2 into 31 means 310.8 into 10 to the 4, which is Iyy plus area A R square, R means Cyy, this is Cyy into S by 2 whole square. So, from this I can find out 23.6 plus S by 2 is equal to this, and from this S is equal to becoming 183 millimeter, right. So, in this way we are getting spacing as 183 millimeter. Next, what we will do? Now, we will design the lacing using single lacing system, right. So, if we see the two section is given and we are providing lacing, right. Let me draw first, then it will be easy to understand, right. So, in this way it is going on. Okay. So, first we are using single lacing system inclined at 45 degrees. So, this is 45 degree, right, this is 45 degree. We are assuming the angle of inclination theta as 45 degree, right. So, these two things first step we are assuming, one is that single lacing system and then theta is equal to 45 degree, right. In next step what we will do, as we know we are using ISMC 300. So, from the handbook, that SP6 we can find out the gauge distance G, which is given in the table, right, in SP6. So, in SP6 we can find out G. So, we can find out A. A means which one? A will be basically this one, this distance, sorry, this distance into this distance, this is A. That means this is becoming S, means clear distance between two section, and this is G, which is given in the code, this is G. So, this A will become S plus 2G, right. So, S plus 2G we are making. So, A we are getting 2 into G is 50 and S was 183 millimeter. So, it is becoming 283 millimeter, right. Now, we have to find out L. L means this is the L, right. So, how do we find out? We will find out first. So, this is A we know, right. So, this is A we know. So, we can find out L by 2 and L by 2 we can find out. What will be L by 2? Because here we, if we see, this is 45 degrees. So, this will become 45. So, A by L by 2 is equal to tan theta. So, we can find out L is equal to we will get A by 2A by tan theta. So, in this way we can find out L is equal to 2A by tan theta, right. The way we have find out L is equal to 2A by tan theta. This is total L and this is L by 2, and we are finding from this A by L by 2 will become tan theta. If this is theta, this will be theta, right. So, A by L by 2 is becoming tan theta. So, from this equation I can find out L is equal to 2A by tan theta. So, L is equal to 2A by tan theta. So, 2 into A is given 283 millimeter and theta is 45 degree. So, if we put these values, we will get L as 566 millimeter. That means, L is becoming, this L is becoming 566 millimeter, right. So, again the length of the lacing. What will be the length of the lacing? Length means which one? From this to this is the length, right. So, what will be the length of the lacing? L will become A, this, if this is theta, then L will become A sin theta, right. So, sorry, this is A and this is L. So, this will become A is equal to become L sin theta. That means, L will become A by sin theta, right. So, length of the lacing will become A by sin theta. So, length we are going to find out A by sin theta. So, A is 283 and theta is 45 degree. So, we can find out from this the length of lacing as 400.2 millimeter, right. So, in this way we can find out the length of the lacing. So, step by step we are proceeding to find out the dimension of the lacing, right. So, what we have done? First we have decided the angle of inclination, then we have found the length of the lacing and the spacing, right. Next what we will do? Now we have to find out the what do you call, the thickness and width of the lacing, and before that we have to check as per the codal provision that this L by RC minimum should become this, right. Now, we know RC minimum, which is for individual channel, this is RYY, it is 26.1, because we have to check the, see, if this is going like this, we have to check whether this is strong enough, means local buckling should not occur. How to ensure that? From this, the radius of gyration of this portion, right, and this portion we can make ensure through this equation that L by RC minimum should be this, and as per the codal provision this should be less than 0.7 into lambda max, 0.7 into lambda max, and lambda max we got already earlier, lambda max was 50.8. Lambda max means the maximum radius of gyration, sorry, maximum slenderness ratio of the main member, right, of the built up section. So, in this way we are finding L by RC minimum is becoming 21.69, whereas it should be less than 35.56. So, we can say this is okay as per codal provision, In clause 5.7.6 it is told that L by RC minimum should be less than 0.7 lambda max, and now 0.7 lambda max is becoming 35.56 and L by RC minimum is becoming 21.69. So, this is less than the 0.7 lambda max. So, this is okay. Now, what we will see that effective length of the lacing bar. We know the length of the lacing bar, that is 400.2 millimeter length we found, 400.2 millimeter. So, for single lacing system with riveted joint we know LE becomes L, effective length will become equal to the L. So, the effective length in this case is becoming 400.2 millimeter, right. Next, what we will do? In next step, we have to assume some rivet diameter. So, let us use 20 mm diameter of rivet, right, and power driven soft rivet let us use. So, what we will get? We will get the minimum width of the lacing as per clause 5.7.3 of IS 800 as 60 mm. Minimum width of the lacing we are getting 60 mm, right. So, let us use B is equal to 60 mm of the lacing width, let us use 60 mm, okay. And then in next step what we will do? We will find out thickness. A thickness should be for single lacing system L by 40, means it should be greater than L by 40. So, L is 400.2 and 40 is okay. So, we are getting 10 mm. So, we can try with the lacing bar as 60 by 10 dimension, okay, and using 20 mm diameter power driven soft rivet. So, these are the unknown things what we supposed to get. Now, we are getting that dimension of the lacing will become 60 by 20 using 20 mm power driven soft rivet, right. Next, what we will do? Next, we have to check the maximum slenderness ratio. Maximum slenderness ratio for the rectangular bar, we know in earlier equation we have seen that will become finally LE root over 12 by T, and for other type of section shape, suppose angle section or some other section if we use as a lacing bar, then we have to find out lambda max from the equation that LE by R, where R is given in the table, right. So, from this we are going to get LE as 400.2 and T as 10. So, if we put those value, we will get 400.2 into root over 12 by 10 is equal to 138.6, which is less than 145. So, this is okay. If the lambda max is greater than 145, then what we have to do? We have to increase the dimension of the lacing system. Dimensions means here we are seeing that we cannot change other things but the thickness, because other things if we change it has no meaning, because this is fixed, right. So, thickness we have to increase if we cannot satisfy this one. So, to satisfy this one we will do lambda max is equal to LE root over 12 by T, and accordingly we will check what is the value is coming. So, now we will check the maximum slenderness ratio. Maximum slenderness ratio what will be? That for rectangular type of bar we will get LE root over 12 by T. Otherwise, if we have say lacing bar as angle like section or channel like section, then we have to find out LE by R, where R is given in the code for a particular dimension of the section, right. So, here we are getting LE root over 12 by T. So, if we put the value LE as 400.2 and T as 10, we are going to get 138.6, which is less than 145. So, it is okay, right. Now, if this lambda max is becoming more than 145, what we have to do? There will be only possibility is to change the thickness T, because if we change width there will be no meaning, that means we are not able to decrease. So, to decrease this we have to increase the thickness. So, if the lambda max is coming more than 145, then we have to increase the thickness so that it becomes less than 145. So, in this way we have to adjust, right. So, as per the closure provision in clause 5.7.2.3, we have to see whether lambda max is becoming less than 145 or not. And then what we will do? Then we will find out what is the lambda lacing and accordingly what is the permissible stress, permissible compressive stress. So, for lambda lacing 138.6, permissible compressive stress we will get from this, that is from table 5.1, table 5.1 of IS 800. There it is given for different lambda, the value of sigma AC has been given. So, for 138.6 lambda lacing we will get permissible compressive stress as 51.84 MPa, right. Next what we will do? Next we will find out the force, shear force which is coming into lacing as 2.5% of the axial force, that is coming 25 kilonewton, because as per the codal provision we know that transverse shear on lacing will be 2.5% of the compressive force. So, 2.5% of the compressive force, that is becoming 25 kilonewton. So, now for single lacing system we know this force will become V by 2 sin theta, because as this is in angle it is there. So, if this is the main bar, then we know if this is there we have one system is like this and another will be coming like this. So, F will become V by 2 sin theta, right. So, V is 25 and theta value is 45 degree. So, we can find out 17.68 kilonewton. Okay. So, in this way the force on lacing bar can be find out, but remember this will be different for double lacing. And what will be the value, means F will become for double lacing, as we remember 4 sin theta, because double lacing is there. We will come later when we will design with the double lacing. In step 10 what we will do? We will check the compressive stress and tensile stress. Tensile stress, how much it will develop? This we know, F by B minus D into T, right. So, F is 17.68 into 10 cube, this is the force, and B is 60 mm and D the diameter of the rivet, that is 20 mm diameter of the rivet. So, gross diameter will become 20 plus 1.5 mm. So, 21.5 mm, right, and T is given 10 mm. So, if we calculate this we will get 45.92 MPa, and allowable tensile stress in the member, as we know, this is 150 MPa, because 0.6 into Fy is 250. So, 0.6 into 250, that is 150 MPa. So, allowable allowable tensile stress, this is becoming 150. So, this is okay. That means developed tensile stress is less than the allowable tensile stress. So, the assumed dimension or calculated dimension of the lacing bar is completely okay. Now, we will check for the compressive point of view. So, in compressive stress what will be? That will be simply B by, means F by B into T, F by B into T. So, F is this one 17.68 into 10 cube, by B is 60 and T is 10. So, this is coming 29.47, and this is less than the permissible compressive stress. Permissible compressive stress we found from the table as 51.84. So, this is less than the permissible compressive stress. The developed compressive stress is coming 29.47 and allowable is 51.84. So, it is okay. So, the assumed dimension is perfectly okay from all point of view. All point of view means from compressive point of view, from tensile point of view, from buckling point of view. Okay. So, we have checked as per the corporation. Next what we will do? Next is the last step, that is end condition, end connection. design of end connection in between lacing and the mainframe, right. So, as we have assumed that rivet diameter as 20, so we can find out the rivet value for single shear as tau Vf into pi by 4 into d square. Now, tau Vf is 100, we know the allowable shear stress tau Vf is 100, right, and gross diameter is 21.5. So, we can find out the rivet value for single shear as 36.3 km. Similarly, in case of bearing, that rivet value will become sigma Pf into d into t, where sigma Pf is 300, this is d and t is the thickness of the lacing. So, this is becoming 64.5 km, right. So, now the rivet value will become lesser of these two, 36.3 kN and 64.5 kN. So, lesser of these two is 36.3 kN. So, this is the rivet value, and number of rivets will be required as per the formula 2f cos theta by r. That also we have shown why 2f cos theta in case of single lacing. So, 2 into f into cos theta by r. This is becoming 0.69, that means 1. That means the number of rivets is required 1. So, with this calculation, let us see what will be the detailing of the lacing system. So, what we have seen that one lacing is here, means main member, and say this is the lacing system. Now, right, this is the lacing and this is the member, main frame member. It is not going to be too, means according to scale I am not able to draw here, however, just I am giving a free body diagram. Now, this is the lacing. So, this is one channel section, say it is placed like this. This is ISMC 300, right. Similarly, another channel section, if I see the cross section, this is another channel section. So, this is also ISMC 300 and this distance is 183, that is the spacing 183 mm, right. And now, this is called L, which is 566 mm, and this distance is L, that is 400.2 mm, right. Other things is, now one rivet we are going to provide in each joint. So, this rivet is 20 mm diameter power driven shop rivet, right, and this angle is, we have designed considering this angle as 45 degree, and the dimension of this lacing is 60 by 10 mm, right, and this also we know, this distance, gauge distance we know, means A, which is A is equal to S plus 2G, that is becoming 283. So, these are the things which remain. So, in this way we can finalize the design. So, from the means when one is told to design the lacing system, means the built up section, that means this will be the answer. That means we have to show in drawing, mean in terms of drawing we have to show what are the detailing, right. So, we can see here in short we can say that use 2 ISMC 300 at 35.8 kg per meter channel section back to back with a spacing of 183 millimeter and provide 60 by 10 mm flat bar for lacing inclined at 45 degree to the compression member connected by one number of 20 diameter power driven shop rivet at each end, right. And if we show the drawing, we have to show that what is the spacing, what is this L value, and of course this theta and other things we have to show, the section, etc. Now the same problem we will design by the use of double lacing. That means in first half what we have seen, that first we have found the built up section, appropriate built up section to carry the required amount of load, that is 1000 kilonewton. Then we have designed the built up section using single lacing system. Now we will do the same thing using double lacing system. The purpose of showing this is what is the difference in design of lacing system for using single lacing and using double lacing, just to know what are the difference we used to follow, right. So if we see, so here L will become this one, right, this is L and this is theta, we have to assume. So in first step what we will do, that we will assume that we are going to use double lacing system and say we are using with an theta of 45 degree, that means angle of inclination we are using 45 degree. Okay. So in first step, in earlier case we use same thing using just single lacing system with 45 degree angle, here double lacing system but 45 degree angle. Let us see what are the difference we are going to get it, right. In step 2 what we will do, we will find out A in similar way, that 2G plus S and this is coming 283 millimeter, and similarly we can find out L, and here what will be L? L means this one, that means if this is total means 2L, this is again L, right. So we can find out L as from this triangle, if this is theta, this is becoming theta, so and this is A. So from this triangle we can find out the value of L, which will be L is equal to A by tan theta, where A is 283 millimeter and theta is 45 degree. So we can find out L is equal to 283 millimeter, right. And similarly the length of the lacing can be find out, that will become A by sin theta, that will 400.2 millimeter. So difference with single lacing system is that only this one, other things are same. A was 283 millimeter and L was also same, right. Now let us see what are other difference we are getting. In step 3 what we will do, we will check the L by RC minimum ratio, which should become less than 0.7 lambda max. Here L is 283 and RC minimum is 26.1, because RYY is 26.1 from the table we got, and from this we can find out that L by RC minimum is 10.84, which is less than 35.56. So it is completely okay, right, as per the clause 5.7.6 of IS 800 1984. Now in step 4 means in next step we will find out the effective length, and in case of double lacing system with riveted ends, we know effective length will become 0.7 L. In single lacing system it is L, and in double lacing system it is 0.7 L for riveted joint. For welding joint, for single lacing system it will be again 0.7 L, remember. So all these are given in the code, we have to follow the code itself. We do not have to remember much, only thing we have to follow the coded provision in 5.7, clause 5.7, all details have been given, right. So the effective length we are going to get 280.14 millimeter. Next what we will do? Next we will assume some diameter of the rivet, say same diameter of rivet we are going to use, say 20 mm diameter of power driven shop rivet we are going to use. So, if we use, we know the minimum width of the lacing will be 60 mm as per the clause 5.7.3. So, the width we are going to fix as 60 mm, and then thickness for double lacing system, this should be greater than L by 60. In case of single lacing system, it was L by 40. So, this is the difference. So, thickness we are going to get 400.2 by 60 is equal to 6.67 mm. So, we can use 60 by 8 mm flat bar for lacing connected by 20 mm diameter power driven shop rivet. So, earlier case in single lacing system it was 60 by 10, and here we are going to use 60 by 8. So, in double lacing system we are reducing the thickness. Now, let us see from other point of view, from buckling and other point of view, whether it will be able to carry that much load or not. The compressive stress, the tensile stress, whatever will come, whether this dimension will be able to carry that much stress or not. Those things we have to check. Now, maximum slenderness ratio for this we will find out, that is LE root over 12 by T, that is becoming LE is becoming 280.14 into root over 12 by 8. So, this is becoming 121.3, which is less than 145. So, this is also okay as per the clause 5.7.2.3. Lambda maximum should become less than 145. So, this is okay. Now, here you observe that LE, as LE is less. So, if I going to reduce the thickness also, finally the ratio is going to less than 145, right. So, some advantage is there for double lacing system, but material will be require more. So, we have to see what is the load, and we have to make use of material from economic point of view. Whether we will be going for double lacing system or single lacing system, we have to see what are the amount of material we are going to use for the lacing system. From that we have to make. In step 8, what we will do? We know lambda lacing is this. So, what will be the value of sigma SC? Now, sigma SC means that allowable compressive stress, which we will get from table 5.1 of IS 800 1984, right. So, sigma SC we can find out from this table 5.1, that is 63.09 allowable compressive stress or lacing sheet. In next step, what we will do? We will find out the transverse shearing force on lacing. Transverse shear will be 2.5% of axial force. So, that will become 25 kilonewton, and force on one lacing bar will become F is equal to V by 4 sin theta, whereas in case of single lacing system it was V by 2 sin theta. So, force will definitely will become very less. That means the size of the lacing system can be made very less. However, if we use the 20 mm diameter of power driven shop rivet, then the width is fixed, minimum 60 mm. So, we cannot reduce the width of the lacing, only we can reduce the thickness, right. So, all these things we have to see. Unless huge load is coming, we do not generally go for double lacing system, right. So, in next step what we will do? We will check for the tensile stress and compressive stress. So, in case of tensile stress, the sigma at T will develop F by B minus D into T, where F is this one 8.84 into 10 cube Newton, B is 60 and D is 21.5 and T is 8. So, if we calculate, we will get 28.7 MPa, which is less than 150 MPa. So, it is much safe, much below than the allowable stress, which is 150 MPa, right. Similarly, for compressive stress on each lacing bar, we will get F by Bt. F we know and Bt. So, we are getting 18.42 MPa. This is also much less than the permissible stress. Okay. So, the calculated thickness and width of the lacing bar for double lacing system is quite okay to carry that much load, right. Next, the end step is end connection, the final step, the last step. So, what we will do? We will find out the rivet value for 25 power driven sub rivet in single shear, that will become tau Vf into 5/4 into d square, and tau Vf is 100 and pi by 4 d square, and this is coming Newton. So, if I divide by 1000, it will become kilonewton. So, this is coming finally 36.3 kilonewton. Similarly, in bearing we can find out that sigma Pf into d into t, sigma Pf is 300 and d is gross diameter 21.5 and t is thickness of the lacing. So, if we calculate, we are going to get 51.6 kilonewton. So, thus we can find out the rivet value as the lesser of these two, that is 36.3 kilonewton. So, the moment we are getting rivet value, we can find out the number of rivets required. Number of rivets will be 2 f cos theta by r. 2 f is 8.84 and theta is 45 degree and r is 36.3. So, this is becoming 0.34. That means at least one rivet will be required. So, number of rivets is becoming 1. So, here we are seeing that we are designing in a conservative way, right, because everywhere we are seeing the allowable stress is much higher than the developed stress in terms of compressive stress, in terms of tensile stress, in terms of the slenderness ratio, in terms of number of rivet required. So, for this case at least we can say that if we use single lacing system, it will be economic. However, it may vary case to case. It depends the length of the built up section, spacing of the built up section and the loading, compressive load, because 2.5% load is going to carry by the lacing system, which was for shear, which has to be checked. So, all these things we have to see and we have to decide. So, basically the design engineer can choose from their experience whether it will go for single lacing system or double lacing system. So, finally, if we see that we can use 2 ISMC 300 at 35.8 kg per meter channel section back to back with a spacing of 183 millimeter and provide 60 into 8 mm flat for lacing inclined at 45 degree to the compression member connected by one number of 20 millimeter diameter power driven sub rivet at each end. So, only difference we are getting from single lacing system to double lacing system is the thickness, just we have reduced the thickness. So, if we give the dimension, this will become, this is 45 degree, this will become 400.2 millimeter and everywhere 125 PDS rivet will be required, and then this is coming 283 millimeter and the size will be 60 by 8 mm plate, and this will be ISMC 300, right. So, when we will show in design, these are the necessary data which we have to show, right. Now, you have seen that what are the design steps we are going to follow for designing of lacing system along with the built up section, right. So, what we have seen that we have to remember lot of things in terms of codal provisions and we have to follow a step by step method for designing this. And also we have seen that once we go for designing, again if we want to redesign for making economic, it is a lengthy process. This is a long process will be involved to design the same thing. So if we have a software like things which we can develop at our own, then we do not need to remember all these codal provisions. So in software, if we can make that, first we will see what are the steps, and accordingly we will develop a software, and all the codal provisions we will keep on checking in that software. Then if we start designing of a lacing, we do not have to remember anything about the codal provision, right. This is one thing, the advantage of software. Another thing is that we will go on trial and error method, means we will go on checking. Say suppose we are giving some dimension, then we are checking whether it is okay or not. Then again if it is okay, again we can reduce the dimension, then we can check once again, and if it is not okay, then we can increase the dimension. So in this way, again and again if we repeat, then we will get an economic size, which is very much important for designing of an effective lacing system. So with this I like to conclude today's lecture about the lacing, and in next lecture we will start the battening system.